All right, so welcome back to che205. This is part 3 of solving nonlinear problems, nonlinear optimizations using spreadsheet calculation. So we particularly talked about example 9.5 in the textbook, and we talked about this reaction. We converted, we found the exact solution, which was like this. We use initial condition. We found that the exact solution looks like this. But we also talked about in the lab, if you really want to measure k, the rate constant, you have to do experiments. And by doing so, you get the table like this, where you have the experiment number, time, the time at which the concentration was measured, the temperature, and the concentration. Okay. So we said there's a typo in the textbook, so this parenthesis should be actually moved to the end, like so. So this is the correct one that I have on the bottom in red. Okay, so what I'm going to do next is basically to solve for C1 and C2. So C1, C2 are sort of related to this rate constant. I mean, rate constant is related to C1, right? And if you plug this C1 and C2, if you plug this K into the original reaction concentration here, then you get the concentration of A is related to nothing but C1 and C2. So there's no K anymore here because we replace K by C1 and C2. So that's the equation we're going to get. And we're going to solve for C1, C2 using the fit or regression, called regression in math, which means you're fitting a curve to a bunch of data points. Okay? So how we do this is we create a spreadsheet like this. We have the experiment number, we have the time, we have the temperature, we have the concentration exactly like the table. So we're going to start with some initial guess. Let's say my initial guess is, I don't know, let's start from 1 and 1. Okay. And for every experiment, I have to calculate the concentration using the guess of C1, C2. So you plug in C1, you plug in C2, you plug in the time, you plug in the temperature. For every experiment, you get the CA back. And that's what I do here. In other words, this is going to be exponential of minus B1, which is C1. So it's minus C1 times T, it's right here. And then times exponential of minus C2 divided by temperature. So here's C2 divided by temperature, and C1, C2 are the blue and purple cells right here. So I'm going to drag this guy down. Okay, and I've calculated CA for all these values, given the C1 and C2 as guess. Okay, so then I can calculate residual. So residual is nothing but let's say in this case I'm gonna have the difference between left hand side and right hand side. So it's going to be left hand side minus right hand side. So here's left hand side E3, right? So this is blue cell, which is CA calculated. I'm sorry, actually the right hand side minus left hand side. So right hand side is the calculated, it's the blue cell, minus D3 is the green cell. So this is the calculated minus minus the experimental value. So this is the experimental value, right? And this guy is the calculated minus experiment. So with that, we're going to drag this guy down so we get the residual for all 5 equations, or 6 equations, or 6 reactions. Then we're going to square them. So here's the square of residual. So we can basically write it as, this guy squared. I'm going to scroll it down. And we're going to lower the number of digits. Okay, there you go, maybe up to 3 digits. So move it back. Okay, so I have the residual squared, and this is the sum of the residual squared. And as the previous problem, exactly like the previous problem, we're going to minimize the total residual, which means we're minimizing each individual residual, because when you minimize the sum of numbers, which are all positive, that means you're basically minimizing each number, and that means you're minimizing each residual. Okay, so minimizing this subject to no constraints. So we're going to go to data, solver, And we're going to minimize this cell, which is G9. This is a minimization problem, and the variables we're changing is, or are actually, these two cells, so B1 and D1. So B1 comma D1, you see that. Well, now in this case, we don't check this out because these are the constant, these are the concentration, so those can be negative. So this time I'm not going to check this. And this is nonlinear optimization. You can also do the same thing with maybe 100 seconds and 100 iterations, some initial precision there. So I'm going to hit OK, and we're ready to go. Let's say initially I assume this is 1 on 1, but could be negative, right? These are not the concentrations, by the way. These are the constants in, this is the constant I'm trying to fit, right? This actually, both of them go to the rate constant. So C2 could be negative. C1 cannot be. So I know this one. But for now, because because C2 can be negative, you cannot just say which one is positive, which one is negative. We can say both of them could be negative. Although we know C1 cannot be. C2 can be. Okay, so let's go back to the spreadsheet. I have to move this over, move this window over here, and this back there. Okay, so let's cancel this again. Go back to solver one more time. We're minimizing B10. That's right. That's let me see. So this is the sum of the residual squared, and this is, well, okay, this is like the average. Yeah, it doesn't really matter if you're minimizing this or this. This is nothing but the total residual divided by, maybe 6 or 6 minus 2. Doesn't really matter. So I'm going to actually move this guy to here. And we don't need this anymore. So let me clear the content. Okay, so we're going to minimize G9 in fact. Let's go to solver. Minimize cell. So it's going to be this cell. Okay, and the variables are this one and that one. I think everything is fine. They can be negative, and I'm going to go solve it. Objective cell must be a formula. That's G9. I clicked on F9. That's incorrect. So let me correct this one. It's going to be G9. There you go. So the solution is going to be 900 here, 900 there. And the error goes down to almost 0. You see that these residuals are 0. That means the fit almost matches the experimental values. So these are the experiments, and these are what we calculate: 9.8, 0.98, 0.99, 0.98, 0.99, 0.54, 508, 22, 25, 56, 49. It's almost close. I think it's good. So we're going to keep it. All right. So this is the solution. We found a fit to the experimental values using this equation. So now you know how to fit any curve to any set of data points using solver. That's called regression. So if next semester any of the professors ask you, okay, we want to go and do this regression or fit this line to these data points, you should be able to do it with a spreadsheet using solver. Okay, so you know how to do the fit. You know how to solve nonlinear equations. You know how to find for the roots using the solver. So solver, it's not just really optimization. You can convert a root finding to optimization problem by defining some error and calculate the residual squared, exactly like what you did in this problem. Okay, so the solver is really powerful. It's not just optimization, it's also root finding, solving system of equations, regression, all of this good stuff. Okay, so I think that ends chapter 9. Thanks so much for watching. Stay tuned for the next video on chapter 7, which is all about regression.